Hey everyone, this is Vinod Iyengar. I'm the head of product at ThirdAI. We've been in business for about a couple of years. I joined a year ago. Prior to this, I was a VP of product at a company called H2.ai. So I've been in the AML space for the last 10 years. So ThirdAI, our mission is to democratize generative AI. It's a well-abused term. Everyone talks about this, but what do we really mean by that? So we'll get to specifics of how we do this. So when you think about generative AI and specifically when it comes to LLMs, which is what we are seeing a lot of usage on, we're seeing that amongst all the noise out there, the three sort of big buckets of use cases customers are doing. Starting off with enterprise or enterprise assist type of use cases. These are ticketing systems, toolings like Alex and Justin mentioned earlier. We see the second bucket of use cases around FAQ bots, customer service chat conversations, co-pilots, so to speak. And the third bucket is around content generation. That code generation as well, content and code. This could include marketing content, agent responses, FAQs, and so on. But the fundamental aspect of all of these is you still need to bring your own data. And this is where a lot of the privacy enterprise concerns come into play. So you're essentially looking at bringing your own data and doing generative AI. So we've been all told that this is what the hello world looks like, right? Hello world of generative AI is bring your data, give it to an embedding model, generate the vectors, throw it to vector database, and voila, you get a parrot with an LLM. You have built RAG, base of RAG. This is the base of all generative applications. So I would say 95% of most companies, when they say they're doing Gen AI, they're basically doing a variant of this. So this is great. This is the hello world example, but in reality, it looks something like this. You can't just throw the data. You need to first bring your data from all bunch of sources. This could be multimodal data, unstructured, structured, a combination of data lakes, documents, code, log, etc. At this point, you are looking, okay, how do I then chunk this data, right? It's all great if your data is JSON, you can just directly ingest it, perfect. But if you're looking at PDFs, logs, code snippets, some structured data, tables, and it's a whole big mess. There's a lot of open source libraries out there which are doing like chunking, parsing, recursive extraction, and so on. Unfortunately, most of it is pretty fragile. After, let's say you've done all this, then you go and say, okay, now I need to tag my entities, extract any NERs, PIIs, redact information. I need to then find the metadata about this. People are using graph databases, using LLMs for this task even, and then other kinds of models. After this, you then go pick an embedding model of your choice. There's a lot of great open source models. You can use OpenAI if you like. You have to pick your choice of dimensions, how much that impacts your cost. I'll get to that in a second. Let's say you pick something, you got the embeddings, at which point you pick a vector database, throw it into it. Your memory has blown up massively. If you're doing a hello world with a single PDF, that's one thing. But if you try to do even like a few gigs of data, enterprise data, you're looking at a big chunk of change going into vector database in the embedding process. Once that's done, you now can't just give it to LLM. You have to now see, okay, is there any issues with my data? You need guardrails. Am I accidentally leaking PII information? Am I accidentally spewing your toxic content? Is there any other context? Is my model actually doing what it's supposed to do? Is the agent actually solving the purpose it's built for? After doing this, you'll get your enterprise AI app, right? Where it may be a chatbot or an agent assist, co-pilot, you name it. The crux of all this is you are now spending a lot of money on GPUs. Of course, if GPUs are available, many regions they are not. There's shortage. Your data is moving across multiple tools, and there is a lack of privacy. This whole process is hard to customize because if something goes wrong, where do you go fix it? Do you fix the embedding model? Do you go fix the vector database? Do you fix your chunking? It's unclear where the issue is. And then the cost of this whole enterprise exercise can be very high too. And finally, is it all usable? We found that in one of our customers, actually a large enterprise, they tried to do this. A simple chatbot. They wanted a simple chatbot on PDFs and a bunch of data. It turned out the latency was about 15 to 20 seconds for every query. So you go from a simple, I want just a ChatGPT on my data to getting a long latency, which becomes unusable. So that's what we are trying to solve. At ThirdAI, we said, how do we bring all these things together and build it into a single package, which can build all the predictive models, do all the advanced parsing, chunking, index and search your data very, very fast without needing embedding models or vector databases, do the re-ranking, and then pair with any generative model of your choice. By doing this, we are able to now dramatically reduce the time it takes to build these generative apps, reduce the cost and the latency. Now, you might be wondering, how is this all possible? Is it even true? And I have some data points. I'll show you a couple of examples. So first thing is, I'll talk about the scale and cost passive. We took basically 10 million documents. To do this with any open source model or even OpenAI would have taken at least a day, or if not more hours of coding. We were able to tune this all on a single MacBook. On my MacBook, basically 16 gigs of RAM, under 4 minutes. And not too shabby precision, right? We are able to get pretty good accuracy. And this is fine-tunable. I'll get to that, why that's interesting in a second. But this is just out of the box, we can get pretty good accuracy. So that starts for the index and retrieval, which is the main crux of your RAG pipeline. After that, we have a whole suite of basically an LLM firewall. So again, built with the same stack, we can build all these models built in: PI redaction, toxicity detection, prompt attack prevention, concept. All these tools are available, so you don't need to go step out, use another service. Again, very low latency. And when we talk about latency, we're really talking about like under 5 to 10 milliseconds for pretty much all the foundation models that you build. And these are basically your classic BERT style models that are used for a lot of the workhorse, which are the workhorse for a lot of the tasks, right? And we can do under 1 core for inference, 4 cores for training, and you can even go up to like 5,000 tokens if you want. So you can take a large document and run it through these fundamentals. Now, the question is, why are we uniquely placed to do this, right? What is the secret sauce? So we'll spend maybe a few minutes just talking about that. So the fundamental sort of non-obvious insight that what I found it on is the fact that we are looking in the age of advancements in models like ML are all attributed to the growth in model size. So what we've been told is that as the model size grows up, as the number of parameters grows, you get better models, which is generally true. But now we've reached a stage where we're looking at like a trillion parameter model, which Gemini is rumored to be. They haven't told publicly, so we don't know for sure. But what you find is that 99.9% of the computations in LLMs are actually redundant. We actually published this at ICML last year. I'll link to the paper in a bit. Why is that true? So if you look at a traditional, like a neural network, standard neural network, pick up any architecture, doesn't matter which architecture you pick, you're typically, let's say, getting an input, and if this is a billion parameter network, only a handful of neurons are going to fire, parameters are going to fire for that input. And that changes. Every time you bring a different input, the set of neurons you're going to fire are going to change. So you're going to do this, let's say, a billion parameters. If you do the traditional way, you do a billion parameters forward pass, look at the error, do backpropagation, and then do update. So you're doing 3 billion operations every single input. That means that's too many to do on a CPU or any compute. You need a lot of expensive GPU, and you need to do that. But what if I told you that only about 1% of the neurons actually have meaningful material changes? Meaning 99% of the neurons are actually 0 multiplied by something. So those parameters are being wasted every single operation. But you don't know that ahead of time. So you need to dynamically be sparsing to the whole network. And by doing this, we can reduce the computation by anywhere from 100 to 160x. And you see the benchmarks on the side where we actually took like just pre-training, GPT-style pre-training on 1 billion tokens, and we found that we could be very efficient in training. And the training speed up also comes down to fine-tuning, retraining, and inference. So we get the benefits all over the places. And this is actually research published on multiple, like we have published papers in KDD, MLSys, ICML, NeurIPS. I'll link to all of those. So if you get the slides, feel free to go to these papers. But what that means in practice is that we are able to now completely change this RAG architecture. So if you take the original slide that talked about RAG, what you see is that you have a lot of data being stored in embedding models, which are blowing up the memory space. Then you throw them into the vector database, which is then parsing through the data. The problem with this approach is that you cannot fine-tune. If there is a retrieval error, you cannot go fix it because it's unclear whether you fix the embedding model or the vector DB. It's very difficult to change the embedding model because if you make any change, you need to rebuild the vector database. And then the data movement can often compromise privacy. And last thing is, embeddings are heavy and costly. So the rule of thumb is, if you have a gig of data, your embeddings, depending on the embedding choice you pick, how many dimensions you pick, whether you pick 256 all the way to 1500 with OpenAI, you're going from anywhere from 3x to 15x the size of the data. So your 1 gigs becomes 3 to 15 gigs. So if you have 100 gigs of data, you're looking at 2 terabytes potentially of memory that needs to be stored in the vector database. So your costs blow up significantly. So our approach is to say, what if we treat this as a giant network and instead replace these two steps with one single neural network, which is what we call it a neural DB, because it replaces a neural embedding and vector DB, but it's basically a giant neural network. And if that can basically act as your index, so you index all your data, just like you would index with, let's say, OpenSearch or Elastic, but do with the neural model, so you get the semantic benefit, semantic search, and your memory footprint is 10x lower than what you would do with this traditional model, you still get the benefits. And the nice thing with this approach is that you can, because it's a neural model, you can fine-tune this. Let's say if your retrieval is not correct, you can actually go and update it constantly. And that means that the model gets better over time. And from a cost aspect, what does this mean, right? So we did a benchmark, actually a case study, where we took a large data set. This is PubMed. So PubMed is all the medical abstracts from NIH and all the papers. There's about 120 million text chunks. We took about 35 million abstracts, ran them through this model. So we did the math and we ran it through OpenAI embeddings, and we threw it into Waviate. We can use Pinecone or Chroma, your choice. The cost came up to be almost like, again, extrapolated to about 80K per month to run this index, just to support 20 QPS. So this is not even like, I'm not talking about like enterprise scale, very basic scale. And because the embeddings take your data from 50 gigs to basically 2 terabytes, that's the challenge. So when we ran with ThirdAI NeuralDB, the embedding, without the embeddings, without the vector DB, we were able to get down to 100 gigs of index and the whole stack running in about 4 to 5K. So the cost is basically anywhere from 1/5 to like 1/8 to 1/15, the cost of what it takes. And there's no rate limiting, extremely fast. So at this point, let me jump into a demo and show you what I mean by that. So I'm going to show you 3 things. The first is a simple desktop application. So this is basically, we call it Pocket LLM. So we want to build this just to show how fast this can be. And this is running entirely on my laptop, right? The only thing I'm doing is for summarization, I use OpenAI. I can turn it off and I can still do it all locally. So you can see I have trained about 8 or 10 of these neural DBs, which are all individual RAG applications. So I've trained a bunch of them all on my laptop, going to the cloud, completely private if you want to. And it takes me like a couple of minutes to train a new model, right? I can just upload a PDF, I can do this. So this one, I have basically a bunch of these files from different banks, all their public results. And I'm going to turn this on just for so that the results are nicer. But I'll show you 2 things. First is I can ask questions like this, and you can see this search result is instantaneous. On my laptop, it's like 10 milliseconds. This summarization takes me a few more milliseconds, but this search is very fast. So it gives me the result. I ask the question, gets me the result. I click on this. I can see the answer coming from page 10 of 12. Let's blow this up a little bit so you can see. It's coming from this particular document, and you can see the results. All the table is being parsed. All the parsing, I didn't do any of those things. I just literally loaded it, right? Let me come back over here. I can also chat with this very easily. What are JP and Q2 23 gets the results, gives me the PDFs, and then answers are over here, right? So I can do this very easily. Now let's do something interesting. Let me load this model. So our founders are from Rice University. I know there's some Rice students, like alums here as well. So what we did is we took actually their, we got like public documents. There's about 1,000 documents, 1,000 PDFs, all running locally on my laptop again. We loaded it, we trained a model over here. And we're going to ask like questions like HR question. Okay, how to onboard a student. I'm just going to blow it a little bit. So you can see the answers coming up. I click on this. It's coming from this link. I open this PDF. I can see, okay, this is the answer. This is where it's getting the answer. Perfect. Makes sense. Now, let's do something interesting. Let's ask a question like how to motivate faculty to stay. Okay. So for this question, I get an answer which is basically a bit of like an hallucinated answer. So there is no real direct answer in the original corpus. So the retrieval results are all low confidence results. Now, as you know, LLMs like to make up. They never they say no, right? Now, I could prompt it to say that the confidence is low. Don't give me a result. But actually, it turns out, in this case, there is a thing called as faculty retention funds that was created just for this purpose at Rice University. The reason I know that is because our founder is from Rice. He was offered this, so he knows about this. So actually, if I search for this faculty retention funds, you'll find that answer comes up somewhere over here, right? So this exists. But how do I link it? How do I teach this model? So this is where the tuning comes in. Fine-tune. How can I fine-tune this model to know that when I ask for this, I'm really looking for this answer? So first thing I'm going to show, when I search for this, it shows me all these faculty funds, but I want this answer. So I'm going to upload this. So when I upload this, you see the yellow icon coming up. What just happened is on my laptop, the neural network just got updated. It got a nudge. It got updated. So now if I search for this question again, that result became number 1. So you saw live fine-tuning on my laptop for this general report, right? Now let's do the other interesting part. I'm going to take this question, which I was asking earlier, right? How to motivate faculty. Stay. And I can actually turn off the internet, but I won't lose the live stream and the thing, so I'm just going to keep it on. But this teach association also happened locally. And if I open my activity monitor, you would see a spike on my CPU. So now if I go back and ask that original question, hopefully I should be able to get the answer I'm looking for here. There you go. So now I've live fine-tuned this model, fixed the retrieval, taught it the new concept. Now it has fixed forever. So if I save this model is now available for future use. Every time someone else asks this question, this model knows exactly the right answer. So this is how RLHF is done, and we can do RLHF on CPUs so that the model keeps constantly being updated. So this is the Pocket LLM tool. I could have done this just as easily now with code. So let me just show you how easy it is to show on the code. So I'm just going to run a chatbot on the free collab. So the free collab, as you can imagine, is only like, I want to say like 8 gigs of RAM and like 20 gigs of disk, right? So basically can't run anything useful. But because our memory footprint is so low, I'm just running it on completely the free collab, right? And I actually ran this earlier so that we don't waste time looking at code running. But you can see it took like a couple of minutes to run this. So basically, we're building a simple chatbot using the LangChain API. And we threw this ML textbook. And the whole thing took 2 to 2.5 minutes to run. And this is all LangChain stuff, right? Just standard LangChain to do the bot. And now we can run this on the bot over here and ask questions. Okay, what are this? Planning. So it's looking at the result and finding out chain of thought, right? Very easy to do. If I now extend this to, what can I do with this, right? So we actually built what Alex and Justin was showing. You could kind of build like a whole chain of thought-based system as well. So if you want to build your own copilot, we just did that. So again, the benefit for us is because the indexing and retrieval is so fast, we can actually hit those multiple calls. So the challenge with some of these chain of thought top-up use cases is that each query takes time, right? You are doing multiple queries, and multiple queries in turn have big results. And because of that, you end up spending a lot of, the latency is very high, especially with, as these LLMs can be chatty. So you apply those things, because our retrieval is so fast, you can actually use these neural DBs to do the workhorse. They can actually take semantic queries directly. So instead of taking the query to an LLM, breaking it out, and then reformulating the query each time, we can have the query for reformulation at the neural DB level itself. So all the LLM has to do is take this original query and break it out into subqueries. That's the only step it has to do. The semantic understanding is built into the neural DB itself, so it can take this query. So if I actually ran this again earlier, I took the entire LangChain code base, and the task I gave it was, let's build a new retriever function, right? Complete new retriever function. And we're not yet, this could be like a Devin-like thing, but just a simple one. I said, don't use a vector store, simple my retriever function, and wrap it with just to-dos, right? So we could have written regular code as well. And it took about 3 to 4 minutes for me for the whole thing. But again, the main function task was on this part. So the verbose equal to true, I printed. So it took about 5 queries, took the original query, split it into 5 different queries, and then generated the code out of this. So this was the code. very logical function, of course, is the scaffolding. We can now go ahead and build this out if you want to. If you want to build a real copilot for all. So that brings me back. So if you want to get started, there's a whole bunch of notebooks in the link. I put the bit.ly, you can, there's all these links are over here. And then there's a ThirdAI package as well. You can start use it to build your own models and GenAI applications. And you can use the Pocket LM tool that I just showed. It's free to download. We can try it. I would love your feedback as you start building this. I think still young company, so we are hoping that will be more prevalent. People will use this as a default. So actually, we put it up on Replit a week ago, and we are already at the most likes on Replit. And actually, this is so fast and low memory that you can run it on the Replit free tier. So you actually start with your like a simple RAG application. So that's a great part. So to answer the question, when you should not use it, again, of course, I'm biased. I think that you should use it by default for everything, because the cost of this is so low. So even if you want to try, so let's say you don't get good accuracy, or you want to improve, try different things, or even you want to use, let's say, a hybrid search. So often people say, let me use an index and retrieval strategy, multiple strategies, right? One may not be sufficient. So you can use us, let's say a couple other vendors, you can use OpenSearch or something else, and you want to do a re-ranker. In those cases, again, this is almost free to try, so cheap to try that it runs locally. There's no reason not to use it as a default, and then of course add other things required. Actually, no. So we have trained it. The smallest we put it out was a Raspberry Pi. So even on a Raspberry Pi with a small enough model, we could teach and fine tune. It's fairly, because the whole process again is using dynamic sparsity. So it's very, very efficient to do this on low powered as well. But again, I would say minimum start with like a MacBook class laptop is good enough to start most of the dev. You can do a lot locally. We have two models. One is, of course, if you want to run this on one of the hyperscalers or yourself, we charge by amount of compute you're going to run this on. So you get a license from us. There's a free trial anyone can get. You can use it to try it out. But if you want to, let's say, get a production license, the license, you just specify how much compute you're going to run this on. Let's say you want to run this on 16 cores. You basically say it's 16 cores worth of compute. That's what you buy. And then we don't monitor. It's completely up to you what you do with it. And we found that, like I said, on 16 cores, you can do a lot. And if you can buy, of course, let's say enterprise grade, you might buy like 100 cores. That's enough to do enterprise grade production workloads. So it's very efficient, and we completely, it's completely air gapped. If you don't see anything, you run it all locally on your environment. It is basically, what we do is we create a giant neural network, and the neural network, essentially what it does is we use a technique called learn to index. So it comes from a paper from 2017, actually 15 from Jeff Dean and others. So the idea is that you take the text and map them directly into a hash table, and you keep them into buckets. And then as new text comes in, you throw them into buckets adjacent to it. We use this technical locality, LSH, locality sensitive hashing, to find out what are the nearest buckets which are be relevant for this text. So conceptually, it works very similar to what you do with embeddings and vector DBs. So in embeddings, what you're doing is you're essentially creating into a hyperdimensional space and then throwing into vector databases and then doing cosine similarity. You basically, instead of doing the two-step process, we replace it one step, where the text itself is mapped into a neural network, and the neural network says, okay, which text chunks goes together? So when you ask the question, instead of doing a cosine similarity, I have a learned model that says, I have seen these texts to go together. That's why I'm able to teach it. So when I associate, I'm saying that I'm teaching you, giving you feedback that actually these two texts should go together. So I teach another overall sort of understanding of how this intuition. At a very high level, what we do is, so when we learn, each time we do a pass. So the first time we do a pass, we basically say, okay, let me randomly activate some neurons and then throw it and then see the result. So very similar to how we teach it, right? You do check the error, back propagate. And we do this a few iterations and basically use similar to we sort of taking ideas of information retrieval. So when you search for a web page, you don't go basically look for the entire internet, right? You just say, okay, what is the sub locality of pages that are related to this query, and I'm going to only search those. So let's say, for example, we're searching for ThirdAI, and you search on, you're not going to search the entire corpus. You're going to say, okay, ThirdAI is in the realm of startups based in, let's say, Houston or Bay Area, and you'd find them a set of sub pages and do that. We use a similar technique. So if we treat the entire network, in this case, it's a billion parameter or 10 billion parameters, that's almost at web scale. So you treat that as almost like a giant network, and you only query the network to say which parameters are close enough, using this idea of LSH, which are close enough for my query. Find me only those neurons. And that hashing query is very, very fast. That's like super fast. Once we find those neurons, we only fire those. So we do this before every operation. So every operation, when you get a new input, we say, which inputs are similar to this input I've seen in the past? Give me those neurons, and I'm only going to update those neurons. And there's a paper on this. That's also linked in the notebook. So if you want to read that, more details on that. Currently, it's not open source. There is pre-demos notebooks. So you can try all of those things. We also have a free tier license. So if you want to use it for personal academic uses, you can use it. There's a few benchmarks we published. The company actually was founded before even GPT became so prevalent, right? So the original research, we did like benchmarks against BERT class models, like the original models. And now we have done benchmarks against some of these. Just right now, we focus mostly on the RAG part of it, the index and retrieval. So there we have benchmarks against all the popular embedding services. So we compared against ADA embeddings. You saw the benchmarking against T5, but also the open source embedding models like BGE, and a couple others. So we perform very well on those. Again, the fact that we don't need any GPUs at all. This runs completely on CPUs. That means the cost is very low. And we can fine tune. So let's say zero shot is like outside of the box, we are getting to like say 90% out of the top models. With fine tuning, we feel like you can get actually better than even the top models. So it's a great place to start, low cost. This is, again, I'll link you to the paper, and you've seen those papers, but basically the learn to index idea allows us to take the index to the text. So just take the pointers to the text. We don't need to store the actual text themselves. Okay. So just like in the VectorDB side, you have the pointers to the original raw text that you need to retrieve. We do the same thing. We say, take those chunks, generate the pointers for all those, and store the pointers in the hash table. So you don't actually store the raw text. We store the pointers. So if you could use a neural network to predict text, you could ask it to predict pointer as well. So you can ask the question basically, what is the next best pointer for this text I'm getting? And that's all you're doing. So we're trying to memory map, find pointers that are nearby, close enough to each. First of all, RAG generally is a good place to start because RAG forces the LLMs to provide sources. So you are starting a place where sources are cited, and you can verify. There's ways to there's a lot of RAG evaluation and guardrail frameworks that allow you to check for those. So that's the first part. I personally think that's a great way to go for it. The second is, of course, that tying, again, I'm personally very interested in enterprise use cases where people are building it for a purpose. When you do that, you can tie it to force it to be focused on those use cases. Anything outside of bounds, you basically ignore. The challenge, of course, is when you're building like a Gemini that's available for everyone, then the hallucinations are problematic. Those are tougher to solve because anyone can ask any kind of question. That becomes like a very open-bounded problem. But if you are solving it for a particular task, downstream task, there's ways to basically, with fine-tuning and prompting, and also protections to force it to only answer relevant to the task at hand. And that dramatically reduces hallucinations, at least for those use cases. I wish I had a good answer. I mean, I'm as guilty as browsing constantly on every new paper. Someone posts on LinkedIn and I'm on the rabbit hole. So I don't have a great answer at this point. I'm hoping that AI can help at this point. So maybe someone will build an agent that basically summarizes, or at least says, okay, these are the most important papers you should read. So that way you're not reading every single. So a lot of the time it's on the discovery, right? You read a paper and they're like, maybe this is interesting, but not super interesting. I mean, I already knew the idea. But if someone can vet it out, an AI paper can do a good job there. So time management is hard, I think, for all of us. I mean, I'm in the same bucket. Always, my wife is always telling me, you're like on the phone all the time. What are you doing? So I have a slightly, I guess, controversial take over here, right? So unfortunately, I think we are in the world where GPT is now significantly better, GPT 4.0, right, than any other open source models. And the gap probably will keep increasing. So there was a phase where open source models were really good and like even comparable at beating OpenAI in some other cases. But now we're reaching a stage where the closed source models again have an edge. And it comes down to basically compute and amount of data. The amount of data prep that goes into like OpenAI is basically licensing data and then doing it. Same thing for Google and suppose and Anthropic are doing it. So you're going to have a handful of players just significantly getting better. And that's a challenge. So I'm personally not very excited about this idea that like a handful of companies with closed source models are going to control the whole world, but this is the reality. It might need some breakthroughs on the open source. So Mistral is great, right? Out of the box, it's very good, but neck to neck, if you see GPT-4 just beats it on almost most of the relevant tasks. And that gap will widen when GPT-5 comes out. So we are at the stage. So on the other hand, we should totally be looking at SLMs. I'm a big fan of SLMs for specific downstream tasks. So if we can have a good 7 billion parameter model with a Mistral 7B or Llama 3 and fine tune it for your downstream task, and we've seen that outperforms any commercial model, right? Then you have a really good shot at building like a variety of these models. Again, if you go back to the agent ideas, you could have many of these small models doing specific tasks, and maybe you can have a good orchestrator with GPT 4.0. So you control your data, you control all the downstream tasks, and you control your costs. But right now, it seems that the commercial models are they're edging far ahead, and the gap is not closing. If you think about like all the summarization, Q&A, like closed book Q&A, open book Q&A, all these tasks, these SLMs are pretty good at, and you can actually tune them to be very good at their tasks. So most RAG applications can be solved with SLMs. Again, if you're doing like, let's say complex like agent workflows where you're doing like large action models, those are still a bit out, but most like retrieval type of question. If you're looking for a specific question, answer me from the context, reason with it, basic reasoning, those can be done with SLMs. So I'm excited from that perspective that entire RAG, like for example, our Pocket LLM, but we tested it with the 5.3 model, right? Which is the Microsoft 3.8 billion parameter model, and actually works very well. So most basic Q&A chat can be done on an edge. We can run it on like a phone. It's very easy. So and that can be 100% private. You can essentially have your complete private RAG on your desktop for your own personal applications.